Hello there. So, welcome again. And you can see now we have brought to you another interesting circuit today that is widely used in real world electronic circuit and system design. When whether you are doing and designing a portable application, for example, pulse oximeter, blood pressure monitor unit, temperature sensing, or whatever applications, you will find variety of circuits such as analog to digital converter, digital to analog converter, and in interfacing with them you will find this circuit. So can you identify what kind of circuit it is? We can clearly see this is an operational amplifier which has got two pins, that is positive and the negative. Positive pin is grounded and input is being applied to the negative or inverting input of the amplifier. So this circuit is biased clearly in inverting amplification configuration. So input is here to the negative pin, then output is this pin right here. From the output through the resistor we are feeding back the signal to the negative pin, and there is this capacitor just to provide this bias, the stability for the circuit in order to prevent the oscillation of the circuit. So if you just focus on that to the input, we see that we have got this signal source, and unlike our previous model where we have been using the voltage source, here the input now is the current source, which can be a DC current source or current source with a time varying signal, for example a sinusoidal waveform with a peak or peak to peak amplitude and a frequency, or it can also be configured as a AC current source. Depends on what kind of analysis you wish to perform: transient, DC, operating point, or you want to plot a Bode plot. And then for the frequency analysis you can configure this signal source accordingly. So remember, this is now input is the current to the circuit, output is the voltage. So obviously the transfer function of this circuit is voltage divided by the current, that is output divided by input, and voltage divided by current is resistance R. So this resistance R is going to set the gain of this amplifier, is also called as current to voltage converter or trans resistance amplifier. Since capacitance is also included, this is called as trans impedance amplifier. Output of this circuit is fed back directly to the analog to digital converter on the PCB when you are doing a complete electronic system. So besides that, this current to voltage converter or trans impedance amplifier has variety of applications. Now why I have used LM7332, because it provides me wide range of input and output. We have used the same part in our previous model also, so not necessary you should use this part. You can choose the part suitable to your application. You would like to design this circuit in such a way that this can cover the wide range of input current range to convert satisfactorily and with a constant gain and large bandwidth of the signal frequency, and provides you output accordingly. So you can choose a part, not necessarily this part, but as per your requirement. So obviously I need not model add the spice model of this part. I have done that because I'm doing a real world design and simulating the performance of real world circuit. So this hardware part I have explained you in our previous model, how I got access to the spice model of this amplifier IC, how I installed downloaded it into my computer, and how I added the directory, and how I mapped the symbol pins of the keycad of this part along with or to with its model pins of this part. So that procedure has been already explained in our previous module and so many other previous modules. So if you are new coming here for the first time, you are encouraged to refer back to those modules in order to understand. But here the focus will be to just analyze these through the simulation how this circuit is going to work. So we'll perform a couple of analysis and we'll see how our input current can be converted into an proportionate output voltage set by the resistor gain. Depends, or not necessary you should choose only 100K. You can have any value that is required for your application, okay? But accordingly then you have to choose the gain bandwidth product, do some calculations, but that's not focus. We have also covered those parts in theoretical lectures in our library. Okay, here's the power supply. We are using a dual power supply, VCC and VEE, each plus minus 15 volts. Center point is ground. In addition, we have two capacitors with 100 nanofarad each across the both voltage sources. That is just to reduce the noise or eliminate the noise due to due to the switching action. Okay, so that is there to eliminate the noise. And these pins we are using are the 3 and 2 are the positive and the negative pins. 1 is the output. 4 and 8 are VEE and VCC respectively. So obviously we are using this part and this part from the library. Also explained how to use them from, so refer back to all previous model. So this source I also explained you. So before that, what I did is I would go for always ERC. I click here. I also made sure I don't have any errors, just couple of warnings, which is neglected because it just says symbol U1, that is this one, has input pins in unit B that are not placed. So I'm using only unit A of this symbol from the library of KiCad. It has got 3 units, A, B, and C. So I have skipped using unit B. So because I just need one op amp, one part. So unit B is another op amp that I have skipped. So this is unit A. This is unit C, which are the power pins. That's why only I can skip B, and therefore I can ignore the errors, not errors, rather warnings linked to that. But main part is errors are 0. With that, you see that I have run it and 0 errors. I close it. Then I move to simulator. So I clicked here and look at this. I have performed a couple of analysis here. First is the DC sweep analysis, where I would go and explain you how I did it. So I first chose the new analysis tab, and now I will show you what I did there. So I will click here, edit analysis tab, and then here I amongst various available analysis, I went for DC sweep. I want to sweep the range of input currents and accordingly plot the range of output voltage. So sweep type, I want to sweep the current source. Is there any current source in my schematic? Yes, I1. You remember our KiCad schematic I just showed you. Let me show you again, once again. Where is my I1 here? This is the I1 I am interested in sweeping. Okay, so let's go back to simulator. So come back here again, and here starting value is 0 of that current source. I want to go up to 30 micron. Increment is about 1 micron. So I'm sweeping that from 0 to 30 micron, the current source. I clicked OK with that. And when let me uncheck these two parameters, I will click the simulation button. Once that is done at the room temperature, I am interested in plotting the current of the input current source. So I plotted here, you look, it is going from 0 to 30 microamp. Okay, so that's what my current sweep. And then I'm interested in plotting the output voltage VO. So here So proportionate the voltage is being there. So when the current is zero, in fact, I can zoom in this portion and see if I can have access to that. Let me just zoom to fit and then maybe see that what is the voltage. For example, let's say, well, let me fit on the screen maybe. Yeah, so there is some voltage even when the current is zero, so that voltage is there. Maybe we can try zoom in. Yeah, so it is negative of 100 millivolt range when there is this current right here. Or maybe just fit on the screen. Let me show you. Yeah, here is the current is zero and that I have a negative voltage. So that's a kind of offset voltage you will see. So this is the DC of sweep analysis. And then you can see that for the AC analysis, I obviously chose the new analysis and I have chosen the AC sweep. In the AC small signal analysis, I chose the number of points to be around 1,000 and our start frequency is 1 hertz, stop frequency is 100 mega, and then I clicked OK. And then I simulated this and I got the access to this color, and this is how I did it. Okay, so what I want to do here, show you here, is my gain at DC is 100 dB and I have a constant gain that is set by the resistor in fact. And that is constant up to minus 3 dB point is somewhere here. So that is about 2 kilohertz or 3 kilohertz. So that is a minus 3 dB point. So that's my the total bandwidth here. Okay, so I don't see a unity gain frequency, the frequency at which the gain is dropped to 0 dB. I don't see that. So this is how you can actually see, you perform various analysis and do the simulation. So hope you found this useful. If you did it, share it with others, and do like and stay tuned for more engaging content like this. Till then, wish you happy learning.